step outside on a clear day and turn your face toward the sun. The warmth feels like it arrives the very instant you look up. But the light touching your skin left the surface of the sun about 8 minutes ago, and from that light's own point of view, no time passed on the trip at all. Not 8 minutes, not a single second, nothing. A beam that crosses the entire width of the universe ages by exactly 0. This is what the physics of relativity tells us about light, and over the next couple of hours we will build up to it slowly, one plain step at a time, starting with something as ordinary as how fast light travels. If you like taking a strange idea apart until it finally makes sense, consider subscribing and we will keep going together. The question we're really chasing is an easy one to ask. How can something travel so far and feel no time at all? The warmth on your face on a clear afternoon feels like the most immediate thing in the world. You step into a patch of light and it is simply there, with no gap and no delay, as if the sun had reached across and touched you in the instant you turned toward it. That feeling is honest, and it is worth keeping, because the whole story starts right here, in something you already know by heart. The catch is that the light warming your skin is not new. It left the surface of the sun a little over 8 minutes ago. The sun sits about 93 million miles away. In more careful terms, the average distance from the Earth to the sun is close to 150 million kilometers, a length so large that astronomers gave it its own name, the astronomical unit, just so they would not have to keep writing the full number. Light is fast, faster than anything else there is, but it is not everywhere at once. It travels at a fixed speed, and even at that speed the trip across that gulf takes time. The number works out to roughly 8 minutes and 20 seconds. Hold that for a moment and let it change what you're looking at. When you glance up at the sun, you are not seeing it as it is. You're seeing it as it was 8 minutes ago. If the sun were somehow switched off in an instant, you would carry on feeling its warmth and seeing its disk for those 8 minutes, with no warning at all, simply because the last of its light would still be on its way to you. The sky would look perfectly normal right up until the moment the final wave arrived and the light ran out. This is true of everything you have ever seen. Sight is not contact. It is the arrival of light that left a surface some time ago and travelled to your eye. For the things around your room, that delay is so tiny it might as well be nothing, a few billionths of a second across the space between you and the far wall. But the principle does not change with distance. It only becomes easier to notice. The moon you see is about 1¼ seconds old. The light from the sun is 8 minutes old. The light from the next star beyond the sun, a faint point called Proxima Centauri, is more than 4 years old by the time it reaches you, which means you are seeing that star as it was 4 years ago, and there is no way to see it any fresher. So the night sky is not a snapshot of how things are. It is a layered picture of how things were, each point of light showing its own age, the close ones nearly current and the far ones deep in the past. Look far enough and you're looking at light that began its journey before there were people to look at all. That single fact, that light takes time to travel, is the thread we're going to follow all the way down. It seems almost too plain to matter. Light is fast, but not infinitely fast, and so seeing is always a little bit of looking back. Yet when you take that idea seriously and ask what the trip is like from the light's own side, it leads somewhere genuinely strange, to the claim that for the beam itself, the journey took no time whatsoever. We are a long way from earning that claim. For now, keep the warmth on your face and the 8-minute delay behind it, because the very first thing we need is a real answer to a question people once thought had no answer at all. Before anyone could ask how light experiences time, someone had to prove that light even takes time to go anywhere. And the proof, when it finally came, arrived from the moons of Jupiter. For most of human history, the honest answer about the speed of light was that there did not seem to be one. Light appeared to be instant. You open your eyes and the whole landscape is there at once, near and far together, with no sense that the distant hills arrive any later than the grass at your feet. The great thinker Aristotle held that light was not a moving thing at all, just a state the air took on, present everywhere the moment a fire was lit. Others disagreed, but no one could settle it, because no one could measure it. Anything you tried was over before you could time it. Galileo Galilei, the same man who turned a telescope on the heavens, tried the obvious experiment. He and an assistant stood on distant hills at night, each holding a covered lantern. He would uncover his, and the moment the assistant saw the flash, the assistant would uncover his own. By timing the round trip of the light, Galileo hoped to catch its speed. He found only the delay of human reflexes. The light, whatever its speed, crossed the gap between the hills far too quickly for him to measure. He concluded carefully that if light was not instant, it was at the very least extraordinarily fast. The breakthrough came not from lanterns on hills, but from the sky, and from a Danish astronomer named Rømer working in Paris in the 1670s. Rømer was studying Io, the innermost of the 4 large moons of Jupiter that Galileo had discovered decades earlier. Io circles Jupiter quickly, slipping into the planet's shadow and out again like clockwork, and astronomers use these eclipses as a kind of distant timepiece. You could predict, well in advance, the exact moment Io should disappear. Rømer noticed something that did not fit. The eclipses did not always arrive on schedule. When the Earth, in its own orbit, was moving closer to Jupiter, the eclipses came a little early. When the Earth was moving away, they came a little late. Over months, as the distance between the 2 planets grew, the eclipses fell further and further behind the prediction, by minutes at a time. He saw what it meant. The eclipse itself was not changing. The light-carrying news of the eclipse simply had farther to travel. When the Earth was on the far side of its orbit, when the planets were close, the light arrived sooner. When they were distant, the same light had extra millions of miles to cross, and that crossing took real, measurable time. The lateness was not a flaw in the clock. It was the travel time of light itself, showing up as a delay you could watch accumulate across the seasons. From the size of the delay and his best estimate of the Earth's orbit, Rømer worked out a value. By modern standards, his figure was low, off by around a quarter, mostly because the size of the orbit was not yet known with precision. But the exact number mattered far less than what he had proven. Light was not instant. It had a speed, a finite speed, large but bounded, and that speed could be caught and measured by patient watching. When the astronomer Christian Huygens reworked Rømer's result, he arrived at a figure that, for the first time, put light's speed within reach of the truth. The lanterns on the hills had failed because the distance was too small. Jupiter and its moons gave the experiment a stage millions of miles wide, and at that scale the delay finally became something a human being could see. So light is fast but not infinite. That single correction opens the door to every strange thing that follows, because once light has a definite speed, you can start asking what that speed actually is, and how it compares to anything you have ever moved fast enough to feel. Put a real size to it. The speed of light in empty space is just under 300,000 kilometers every second, or about 186,000 miles every second. Written out as a precise figure, it is 299,792,458 meters per second, a number so exact because it is no longer measured at all. Physicists fixed it by definition and let the meter follow from it, so the speed of light is now a defined constant, the cornerstone the rest of measurement leans on. It carries its own letter in the equations, a lowercase c, for the Latin celeritas, meaning swiftness. Numbers that large stop meaning anything unless you tie them to something you can picture, so tie this one down. In a single second, a beam of light could circle the Earth's equator about 7.5 times. Snap your fingers, and in that snap light has gone around the whole planet 7 times over and started an 8th lap. The fastest jet you have ever heard of crawls by comparison. A rifle bullet, which leaves the barrel too fast to follow with your eye, is slower than light by a factor of around 1,000,000. Bring it closer to home. Light crosses an ordinary room before any instrument you own could register the gap. When you flip a switch and the far lamp lights, The light reaches your eyes in a few billionths of a second, a delay so short your nervous system has no hope of noticing it. That is why light feels instant in daily life. Over the distances of a house, a street, a city, the travel time is real but unimaginably brief, swallowed completely by the slowness of your own senses. The delay only becomes visible when the distances grow enormous, which is exactly why the sky is where light speed first showed itself. Light takes about 1.25 seconds to reach us from the moon, which is why the radio conversations between Mission Control and the Apollo astronauts carried a small but real pause, the words crossing 250,000 miles each way. It takes the 8 minutes we already met to come from the Sun. It takes around 5.5 hours to crawl out to Neptune at the edge of the planets, and the nearest star beyond our own is so far that its light, moving at this blistering pace, still needs more than 4 years to arrive. This is where a unit was born out of necessity. To talk about the distances between stars, kilometers become useless. The numbers grow too long to hold. So astronomers measure in light years, where 1 light year is simply the distance light travels in a year, about 9.5 trillion kilometers. A light year is not a measure of time, despite the name. It is a measure of distance, defined by how far this one steady speed will carry a beam in 365 days. And here is the quiet weight inside the number. Because light is fast but finite, and because the universe is vast beyond any everyday sense of the word, that finite speed becomes a kind of universal speed limit and a universal clock at once. Nothing carrying energy or information has ever been found to outrun it. It is not merely the speed of light, it turns out to be the speed of cause itself, the fastest rate at which any here can ever affect any there. We will earn that grand acclaim later, step by step. For now, fix the scale in your mind, 7.5 times around the Earth in a heartbeat, 8 minutes from the Sun, 4 years from the nearest star. Hold the number as a real thing with a real size. Because the next question is not how fast light goes, but what light actually is, and the answer ties the beam on your face to the magnet on your refrigerator door. For a long time, light was simply light, a thing in its own right, with no obvious family. People knew it could be bent by a lens, split into colours by a prism, and bounced off a mirror, but what it was made of stayed a mystery. The answer came from a direction nobody expected, out of the study of 2 forces that seem to have nothing to do with brightness at all: electricity and magnetism. By the early 1800s, these two were known to be linked. The Danish scientist Hans Christian Ørsted noticed that a compass needle twitched when he ran an electric current through a nearby wire, which meant a moving electric charge produced a magnetic effect. Then the English experimenter Michael Faraday, a largely self-taught man who had started as a bookbinder's apprentice, showed the reverse. Move a magnet near a coil of wire and you drive an electric current through it. Electricity could make magnetism, and magnetism could make electricity. They were 2 faces of one thing. Faraday had a feel for nature but little formal mathematics. He pictured space around a magnet or a charge as filled with invisible lines of influence, what he called fields, reaching out and shaping how other objects would move. It was a powerful image, and it needed someone who could turn the picture into precise equations. That someone was a Scottish physicist named James Clerk Maxwell. In the 1860s, Maxwell gathered everything known about electricity and magnetism and wrote it down as a tight set of mathematical laws. The equations describe how electric and magnetic fields are made and how they push and pull. But when Maxwell looked carefully at what his own equations allowed, he found something hidden inside them that he had not put there on purpose. The equation said that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So imagine giving the system a single shake. A wobble in the electric field makes a wobble in the magnetic field right beside it, which in turn makes a fresh wobble in the electric field a little farther on, which makes another magnetic wobble, and so on. Each one hands off to the next. The disturbance does not stay put. It rolls outward through empty space as a self-sustaining ripple, a wave of electricity and magnetism feeding endlessly into each other, needing nothing else to keep going. Maxwell could calculate how fast this wave would travel. The speed came straight out of two numbers already measured in the laboratory, constants describing how strongly space responds to electricity and to magnetism. He put them together and out came a velocity. When he compared that velocity to the measured speed of light, they matched. That match was the revelation. The wave hidden in his equations, this rolling braid of electric and magnetic fields, moved at exactly the speed of light because it was light. Light was not a separate substance after all. It was electromagnetism in motion, the same force that runs your refrigerator magnet and your wall socket travelling as a wave. Visible light was just the small band of these waves your eyes happened to catch, with radio waves, microwaves and X-rays as the same thing at other rates of wobble. It was one of the great unifications in all of science. Three mysteries, electricity, magnetism, and light, collapsed into one. And the discovery carried a question that Maxwell himself could not answer, a question that would crack the whole subject open within a generation. Every wave anyone had ever met travelled through some material. Sound waves travelled through air. Ocean waves travelled through water. So if light was a wave, the natural next question was simple and seemed unavoidable. A wave in what? Every wave you have ever met needs something to wave in. Drop a stone in a pond and the ripples spread through water. Take the water away and there is no ripple. Speak across a room and your voice travels as a pressure wave through air. Pump the air out and the sound dies, which is why no one can hear anything in the vacuum of space. A wave is a disturbance passing through a medium, and the medium is the thing that actually does the moving, jostling its neighbours along while the wave itself rolls forward. Take away the stuff, and there is nothing left to carry the wave. So when Maxwell showed that light was a wave, the question pressed in at once. Light reaches us from the sun, and from stars unimaginably far away, crossing vast stretches of space that everyone agreed was empty. If light is a wave, and waves need a medium, then space cannot truly be empty. There must be something there, some substance filling all of space, thin enough that the planets glide through it without slowing, yet present everywhere, so that light always has something to ripple through. The physicists of the 1800s gave this substance a name borrowed from the ancients. They called it the luminiferous ether, the light-bearing ether. The ether was not a wild guess. It was the careful, conservative conclusion of people taking their best physics seriously. Waves need a medium. Light is a wave. Light crosses space. Therefore space is filled with a medium. The logic was clean. The trouble was only that the medium had to have a strange and almost contradictory set of properties to do its job. Consider what the ether was asked to be. It had to fill the entire universe, reaching into every gap, so that no corner of space was ever truly without it. It had to be so thin and frictionless that the Earth could plough through it year after year without losing the slightest speed in its orbit, and the planets could circle the sun for billions of years undisturbed. Yet it also had to be astonishingly stiff. Light travels fast and waves move quickly only through stiff, springy media, the way sound moves faster through steel than through air. To carry light at 300,000 kilometers a second, the ether would need to be more rigid than steel, and at the same time so insubstantial that solid planets pass through it like a hand through fog. A substance both stiffer than steel and thinner than the faintest gas is a deeply uncomfortable thing to believe in. But discomfort is not disproof, and the alternative seemed worse. To abandon the ether was to claim that a wave could travel through pure nothing, which made no sense to anyone trained on water and air and sound. So the ether stayed, awkward but necessary, the invisible stage on which all of light's drama was assumed to play out. And the ether made a promise, a testable one, which is what eventually undid it. If all of space is filled with a fixed, motionless ether, then the Earth must be moving through it. We circle the sun at about 30 kilometers every second, so we are forever rushing through this still ocean of ether. And just as a person running through still air feels a wind in their face, the Earth racing through the ether should feel an ether wind, a steady stream blowing past us as we go. That wind, if it existed, would leave fingerprints on light. Light moving along with the wind should travel at a slightly different speed than light moving against it, exactly as a swimmer is faster going downstream than up. The ether had been an idea you could only assume. Now it was an idea you could measure. All someone had to do was build an instrument delicate enough to feel that wind, and 2 Americans were about to try. In the 1880s, in a laboratory in Cleveland, Ohio, 2 men set out to feel the wind that everyone believed must be there. Albert Michelson was a naval officer turned physicist with a gift for precise measurement, so fine it bordered on obsession. Edward Morley was a chemist with the patience to match. Together they built an instrument designed to catch the ether wind, and it remains one of the most beautiful experiments ever performed, precisely because of what it failed to find. The idea was a race between 2 beams of light. If the Earth is rushing through a still ether, then a beam sent along the direction of that motion should behave differently from a beam sent across it, just as a swimmer crossing a river and back finishes at a different time than one swimming the same distance upstream and down. The current helps one way and hurts the other, and the 2 trips do not balance. Michelson and Morley wanted to run that race with light and watch one beam lose. Their tool was the interferometer. A single beam of light strikes a half-silvered mirror that splits it in 2. One half travels down a long arm, bounces off a mirror at the end and comes back. The other half travels down a second arm set at a right angle, bounces and returns. The 2 beams are then recombined and allowed to overlap. Because light is a wave, the recombined beams form a pattern of bright and dark bands, called interference fringes, exquisitely sensitive to any difference in the time the 2 beams spent travelling. A delay of even a tiny fraction of a wavelength would shift the fringes by a visible amount. The plan was to point one arm along the Earth's motion through the ether and the other across it. The ether wind should slow one beam relative to the other, throwing the fringes out of step. Then they would slowly rotate the whole apparatus, swapping which arm faced the wind, and watch the fringes shift back the other way. To make it sensitive enough, they floated the entire instrument, a heavy stone slab, on a pool of liquid mercury so it could turn smoothly without a single jolt, and they took their readings in the quiet, working with a delicacy that let them detect a fringe shift far smaller than the one the ether theory predicted. They ran the experiment carefully at different times of day and different seasons, so that no matter which way the Earth happened to be heading, they would catch the wind from some angle. The prediction was clear, and the instrument was more than good enough to see the effect. They found nothing. The fringes did not shift. Rotate the apparatus however they liked, wait for whatever season, the 2 beams always came back perfectly in step, as if there were no wind at all, as if the Earth were sitting perfectly still in the ether, despite hurtling around the sun at 30 kilometers a second. The light did not care which direction it was sent. Its speed came out the same every way. This was not the small, messy disagreement of an experiment that needs refining. It was a flat, clean zero where a strong effect was expected. Michelson, who had hoped to measure the ether wind precisely, considered the experiment something of a personal failure. He had built the finest ruler anyone had ever made and found nothing to measure with it. But a clean zero is data of the most powerful kind. The ether wind was not weak or hard to find. It was simply absent. Either the Earth was somehow always at rest in the ether, which made no sense, or there was no ether at all, and the very idea that light needed a medium was wrong. The result sat there for years, stubborn and unexplained, a fact in search of a meaning. Set the missing ether aside for a moment and look squarely at the bare result, because the result is stranger than the failed theory around it. Michelson and Morley had shown that light travels at the same speed no matter which way you send it, but hidden inside that finding, and confirmed by every experiment since, is something that breaks every instinct you have about how speeds work. The speed of light comes out the same no matter how you are moving when you measure it. To feel why that is so jarring, start with how speeds normally combine, because in ordinary life they add up exactly as common sense demands. Imagine you're on a train moving at 60 miles an hour, and you walk forward down the aisle at 3 miles an hour. To someone standing on the platform watching you pass, you're moving at 63 miles an hour, the train speed plus your own. Throw a ball forward on that train, and the ball's speed to the platform is the train speed plus the ball's. Speeds add. This is so obvious it feels like it could not possibly be otherwise. Chase after something and you close the gap. The thing approaches you more slowly. Run from it and it recedes faster. Now do the same with light. You're on a spaceship flying through space, and you switch on a headlight. The beam races away from you at the speed of light. Common sense says that a friend watching from a station ahead, toward whom you are flying, should measure that beam moving even faster, at the speed of light plus the speed of your ship, just as the ball gained the train speed. And if you chase a beam of light, racing after it at tremendous speed, common sense says the beam should pull away from you more slowly, the way another car on the highway seems to crawl ahead when you match its pace. Light refuses. No matter how fast your ship flies, your friend measures the beam at exactly the speed of light, not a fraction more. No matter how hard you chase a beam, it retreats from you at the full speed of light, never slowing by even the smallest amount, as though your chase counted for nothing. Run toward a beam at enormous speed, and it still rushes at you at the same fixed value. The number does not budge. Everyone, no matter how they move, measures the same speed for light. This is the stubborn speed, and it is the single fact the rest of this story is built on. The speed of light is not a speed in the ordinary sense, a thing you can gain on or fall behind. It is a fixed feature of the universe, the same for every observer, whatever their own motion. Two people flying past each other at tremendous speed, in opposite directions, will each shine a flashlight, and each measure the very same speed for the light, and for the other's light too. There is no chasing it down and no outrunning it. Sit with how impossible that should be. Speeds add for trains and balls and cars and every moving thing you have ever known. They simply do not add for light. And there is no special trick of the equipment, no flaw to find and fix. Every experiment ever built to test it agrees. The constancy of the speed of light is one of the most thoroughly confirmed facts in all of physics. So we are left with a hard knot. Light speed is the same for everyone, regardless of motion, even though that flatly contradicts the way every other speed in the world behaves. Something has to give. If the speed cannot change when the observer's motion changes, then something else must change instead. For 20 years the knot sat unsolved, until a young man working in a patent office decided to take the impossible fact at its word and ask what the world would have to be like for it to be true. The man who untied the knot was not a famous professor. In 1905, Albert Einstein was 26 years old and working as a junior clerk in the patent office in Bern, Switzerland, examining other people's inventions for a salary, doing physics in the evenings and in the gaps of his working day. He had no laboratory and no fancy title. What he had was the willingness to take a strange fact completely seriously and follow it wherever it led, without flinching when it led somewhere uncomfortable. Everyone else had treated the constant speed of light as a problem to be explained away, a puzzle hiding some mechanism that would, once found, let the world go back to behaving sensibly. Einstein did the opposite. He decided to accept it as a law of nature, a simple given, and then ask what the rest of physics must look like if that law is true. Rather than wrestling the fact into the old picture, he rebuilt the picture around the fact. His paper that year, modest in length and plain in its claims, rested the whole of what we now call special relativity on just two short statements. The first is called the principle of relativity. It says that the laws of physics are the same for everyone moving steadily, in a straight line at a constant speed. There is no experiment you can do sealed inside a smooth-flying ship with the windows covered that would tell you whether you're moving or sitting still. Every steady, unaccelerated motion is as good as any other, and none is the true rest of the universe. This idea was not new. Galileo had grasped it centuries earlier, noting that below the deck of a smoothly sailing ship, everything behaves exactly as it would in port. There is no privileged stillness, no fixed stage against which all motion is measured. That conviction by itself was already enough to doom the ether, which had been imagined as exactly such a fixed stage. The second postulate is the daring one. It says that the speed of light in empty space is the same for every observer, no matter how the observer moves, and no matter how the source of the light moves. This is simply the Michelson and Morley result, promoted from a stubborn experimental fact to a founding law. Einstein did not derive it. He assumed it as a starting truth and built outward. Look at the two side by side and they seem almost too modest to matter. The laws of physics are the same for all steady motion. The speed of a light is the same for all observers. Both sound reasonable, even mild. The genius lay in seeing that the two of them, held together at the same time, cannot both be true unless something we trusted completely is wrong. Here is the collision. If the speed of a light is the same for everyone, but speeds normally add, then the only way out is that the very things we use to measure speed must themselves change. Speed is distance divided by time. If the speed of a light refuses to change when your motion changes, and yet the distance and the time you would normally expect should give a different answer, then distance and time cannot be the fixed, universal things everyone had always assumed. The measuring sticks and the clocks have to bend instead. That was the leap. To keep the speed of light constant for everyone, Einstein realized, space and time themselves must be flexible. Lengths and durations are not absolute, the same for all. They depend on how you are moving. Two people in steady motion relative to each other will not agree on how long a meter is, or how long a second lasts. The price of the constant speed of light is that time and space stop being the rigid backdrop of the world and become things that stretch and shrink. It sounds like a wild claim to rescue a small fact. The first place it shows itself is in something we thought we understood completely: what it means for two things to happen at the same time. Start with a word everyone uses without a second thought: simultaneous. Two things happen at the same time. A pair of firecrackers go off together. Two runners cross the line at once. It feels like the most solid idea imaginable. A plain fact about the world that any honest observer would have to agree on. Either two events happened together or they did not. Einstein's two postulates, followed carefully, break exactly this. They show that whether two distant events happen at the same time is not a fact about the world at all. It depends on who is asking. Here is the thought experiment Einstein himself used, and it needs nothing but a train, two lightning strikes, and the rule that light travels at the same speed for everyone. Picture a long train moving smoothly along a track at high speed. Standing exactly in the middle of one of the cars is a passenger. Standing on the embankment beside the track, level with the middle of the train as it passes, is an observer on the ground. Now lightning strikes both ends of the moving car at once, the front and the back, leaving scorch marks on both the train and the track so everyone can later agree on where the strikes landed. Think about the observer standing on the ground. The two strikes happened at equal distances from her, one to her left at the back, one to her right at the front. The light from each strike races toward her at the same speed. Because the two flashes have the same distance to cover and travel at the same speed, they reach her at the same instant. For her, the verdict is plain. The two strikes were simultaneous. They happened at the same time. Now think about the passenger sitting at the middle of the train, moving forward toward the front strike and away from the back one. The light from both strikes also travels toward him at the same speed, because the speed of a light is the same for everyone, including someone on a moving train. But while that light is travelling, the train is carrying him forward, toward the point where the front flash began and away from the rear one, so the light from the front reaches him first, and the light from the back reaches him a moment later. He sees the front strike before the back strike. For him, the strikes were not simultaneous. The front happened first. Neither of them is wrong. This is the part that takes a moment to absorb. The passenger and the observer are not making errors, and there is no hidden true answer that one of them missed. Each correctly measures what reached them, using light moving at the one fixed speed. The ground observer is right that the strikes were simultaneous. The passenger is right that they were not. Whether the two events happened at the same time genuinely depends on how you are moving. This is what physicists mean by the relativity of simultaneity, and it is the first crack to open in our everyday picture of time. There is no universal now stretching across the universe, no single present moment that everyone shares. Your now and the now of someone moving relative to you can include different events. Two things that happen together for you can happen one after the other for them, with the order itself flipping depending on motion. Once simultaneity goes, the rigid clockwork falls apart behind it. If observers cannot even agree on whether two events happened at the same time, they cannot agree on how much time passed between events either. The single, universal clock ticking for the whole universe, the one Isaac Newton had written into his physics 2 centuries before, simply does not exist. Time has come loose from its moorings, and the next thing to discover is that moving clocks, real physical clocks, actually run slow. If observers in motion cannot agree on whether two events are simultaneous, then they cannot agree on how much time has passed, and this leads straight to one of the most famous and most tested predictions in all of physics. A clock that is moving relative to you runs slow, not because it is poorly built or disturbed by its motion, but because time itself measured along that moving clock's path genuinely passes more slowly than the time you measure. Physicists call this time dilation, and it falls out of Einstein's 2 postulates as a plain consequence, not an extra assumption. The effect is real, but ordinarily far too small to notice, and the reason is the size of the speed of light. Time dilation only becomes significant when something moves at a sizable fraction of that enormous speed. At the speeds of everyday life, a car, a plane, even a rocket leaving Earth, the slowing is so slight that no human sense could ever catch it. Your moving friend's watch does run slow compared to yours, but by such a vanishing amount that across a whole lifetime it would add up to a tiny fraction of a second. This is why the strangeness stays hidden. The world we evolved in moves far too slowly for any of this to show. But the slowing is there, and it grows without limit as you approach the speed of a light. The closer a clock's speed creeps toward that of light, the more dramatically it lags behind. At 9/10 of the speed of light, time runs at less than half its usual rate. Push closer still to 99% and beyond, and the moving clock slows to a crawl from your point of view, its seconds stretching into what for you are many seconds. There is a clean mathematical factor describing exactly how much, written in the equations as a single quantity, that climbs gently from 1 at low speeds and then rises steeply toward infinity as the speed nears that of light. The hardest part to hold is that the effect is mutual, and this is where people's intuition usually rebels. If you fly past me at great speed, I see your clock running slow, but by the very same principle of relativity, you have every right to consider yourself at rest and me as the one flying past. So you see my clock running slow, we each see the other's clock lagging, and neither of us is mistaken. This sounds like a flat contradiction, but it is not, because we also disagree about simultaneity, about which of each other's clock readings count as happening at the same time. The two disagreements fit together perfectly, like two halves of a single consistent picture. There is no paradox once you remember that our nows are different. It helps to be clear about what is and is not happening. The moving clock is not malfunctioning. If you were riding along with it, it would tick perfectly normally, one steady second after another, and your own heartbeat and thoughts would keep pace with it as always. Nothing feels slow from the inside. The slowing is something seen only from outside by someone the clock is moving relative to. Each person's own time always feels perfectly ordinary. The stretching shows up only when you compare clocks that are moving with respect to each other. This is not a trick of perception or a story about how things merely look. It is time itself, the actual rate at which events unfold and clocks tick, and living things age, running at different rates for things in different states of motion. Take this seriously, and the consequences are enormous. A traveller who journeyed at near-light speed and returned would genuinely have aged less than those who stayed behind by minutes, years, or centuries, depending on the speed. The cleanest way to see why this must be true, rather than simply accepting that it is to build the simplest possible clock out of nothing but a beam of light and watch what the constant speed of light forces it to do. To see exactly why a moving clock must run slow, build the simplest clock you can imagine, one made entirely of light. Take two small mirrors and face them toward each other, one on top and one below, a fixed distance apart. Send a single pulse of light bouncing straight up and down between them. Each round trip up to the top mirror and back down is one tick of the clock. Since the distance between the mirrors is fixed and light always travels at the same speed, each tick takes exactly the same amount of time. It is a perfect, honest clock, and its workings are nothing but light crossing a known distance. This is the light clock, and it makes time dilation almost impossible to escape. First, picture the clock sitting still right in front of you. The light pulse goes straight up, hits the top mirror, comes straight back down. Up and down, a tidy vertical path, one tick after another. Nothing surprising. You can time it easily. The length of the path is twice the gap between the mirrors, and the time per tick is that length divided by the speed of light. Now set the same clock moving. Imagine it mounted sideways inside a fast train or a passing spaceship, gliding past you from left to right, while the light still bounces between its two mirrors. To the passenger riding along with the clock, nothing has changed at all. The light still goes straight up and down, because to that passenger the clock is sitting still, and everything inside the ship is perfectly ordinary. But to you, standing outside and watching the clock fly past, the light does something different. By the time the pulse reaches the top mirror, the whole clock has moved sideways. By the time it comes back down, the clock has moved farther still. So from your point of view, the light does not travel straight up and down. It travels in a long diagonal, a stretched out zigzag, up and forward, then down and forward, tracing a path shaped like a wide letter V tipped onto its side. Here is the hinge of the whole argument. That diagonal path is plainly longer than the simple up and down path the passenger sees. The light has farther to go. And yet, by Einstein's second postulate, the light still travels at exactly the same speed for you as for the passenger, no faster and no slower. The same speed, but a longer distance to cover. There is only one possible conclusion. From your point of view, each tick of the moving clock takes more time, because the light has to cover that longer diagonal at the same fixed speed. The moving clock ticks more slowly than the one at rest. That is time dilation, forced on us directly with no escape by nothing more than the constant speed of light and a little geometry. You can even read off how much it slows. The vertical path and the diagonal path form a right triangle, the kind every schoolchild meets, and the relationship between their lengths gives exactly the factor by which the moving clock lags. The faster the clock moves sideways, the longer and flatter the diagonal becomes, and the more each tick stretches. As the clock's speed approaches that of light, the diagonal stretches toward horizontal, nearly endless, and each tick takes almost forever from the outside. The light clock seems like a special case, a strange device built for an argument, but there is nothing special about it. Every process that marks time, a swinging pendulum, a vibrating crystal, a beating heart, the decay of an atom, must slow by the very same factor when it moves, because if any of them kept ordinary time while the light clock slowed, you could compare the two and tell who was really moving, which the principle of relativity forbids. So it is not the light clock that slows, it is time. And if moving clocks must run slow, then moving rulers, as we will see next, must shrink. Time dilation does not travel alone. If moving clocks run slow, then moving objects must also shrink along the direction they are moving, and the two effects are bound together so tightly that you cannot have one without the other. This second effect is called length contraction, and it is just as real and just as strange. An object flying past you at great speed is genuinely shorter, measured along its line of motion, than the same object sitting at rest. Not squashed by any force, not compressed by pressure, simply shorter, because space itself measures differently for things in motion. To see why it has to come along with time dilation, follow a beam of light on a long journey and watch two observers disagree. We already met the muons, particles raining down from the upper atmosphere, but the same logic works for any fast traveller. From the ground, you measure both how far the traveller goes and how long it takes. From the traveller's own point of view, far less time passes because of time dilation. Yet the traveller is still moving at the same speed relative to the ground, and still passes the same start and end points. Speed is distance divided by time. If the traveller agrees on the speed but experiences far less time, then for the traveller the distance covered must be correspondingly shorter. The same trip that is long and slow from the ground is short and quick from the traveller's frame. Space itself has contracted to keep the speed of light, and every speed consistent for everyone. Think of it from the traveller's seat. You're flying toward a distant star at close to the speed of light. From Earth, that star is, say, many light years away, and the trip should take many years. But your clock runs slow as measured from Earth, so by your own reckoning the journey takes only a short while. From your point of view, you are not the one moving slowly through time. You feel perfectly ordinary. Instead, the distance to the star has shrunk. The whole stretch of space ahead of you, the gap between Earth and the star, has contracted along your direction of travel, pulled in close, so that what looked like many light years from Earth is only a short hop for you. Both descriptions agree on what actually happens, you arrive, and your watch reads what it reads, but they split the explanation between slowed time and shortened space. The contraction happens only along the direction of motion. An object racing past you is shortened front to back, in the direction it travels, but its height and width, the dimensions crosswise to the motion, are untouched. A fast-moving sphere would measure as a flattened shape, squeezed along its path of travel while staying full and round across it. And like time dilation, the effect is mutual. To you, the moving object is shortened. To someone riding along with that object, considering themselves at rest, it is your world that is contracted along the direction of relative motion. Each sees the other's length shrunk, and neither is wrong, because they also disagree about simultaneity, about which measurements of the two ends count as being made at the same moment. Length contraction is far too small to notice at everyday speeds, hidden by the same vast size of the speed of light that hides time dilation. A car on the motorway is shortened by a length smaller than a single atom, utterly beyond any measurement. Only near the speed of light does the shrinking grow large, until at the very edge an object would contract toward a flat sheet, its length along the motion squeezed nearly to nothing. So space and time bend together, each adjusting exactly enough to hold the speed of light fixed for everyone. Remarkably, the precise equations describing this bending had already been written down before Einstein explained what they meant, by two physicists who found the right formulas for the wrong reasons. The equations that describe how time stretches and length shrink did not appear out of nowhere with Einstein. They had already been written down several years before 1905 by physicists trying to save the very ether that the equations would help destroy. The strange formulas were correct. It was the understanding behind them that was missing, and that gap is one of the most instructive stories in physics, because it shows that having the right mathematics is not the same as knowing what it means. The first of these was the Dutch physicist Hendrik Lorentz, one of the most respected scientists of his day. Lorentz was wrestling with the failure of the Michelson and Morley experiment, the missing ether wind, and he was not willing to give up the ether. So he proposed a bold fix. Perhaps, he suggested, objects moving through the ether are physically squeezed, compressed along their direction of motion by exactly the amount needed to hide the ether wind. The arm of the interferometer pointing into the wind would shrink by just the right fraction to cancel the effect the experiment was looking for, which is why Michelson and Morley found nothing. An Irish physicist named George Fitzgerald had hit on the very same idea independently, and the notion came to be known as the Fitzgerald-Lorentz contraction. Lorentz went further. To make all the equations of electricity and magnetism come out consistent for a moving observer, he worked out a precise set of mathematical rules for translating measurements of space and time from one moving frame to another. These rules, now called the Lorentz transformations, are the exact mathematical heart of special relativity. They contain time dilation, length contraction, and the relativity of simultaneity, all of it, written out correctly. Lorentz had the right equations in hand years before Einstein's paper, but Lorentz did not believe what his own equations were saying. To him, the contraction was a real physical squeezing of matter as it pushed through the ether, caused by some effect of the ether on the forces holding objects together, and he introduced a quantity he called local time, a mathematical convenience, a bookkeeping trick for moving observers, which he thought was not the true time at all. The true time, he believed, was the time measured at rest in the ether, the one real clock of the universe. He had stumbled onto the correct formulas but kept them chained to the old picture, treating them as a clever patch to preserve a medium that was not there. This is the difference Einstein made, and it was not a difference of mathematics. Einstein took the same transformations and saw that there was no ether to be squeezed through, no true time hiding behind the local time, no privileged frame of rest. The contraction was not a force squeezing matter against a medium, it was a feature of space and time themselves. The local time was not a trick, it was simply time, as really experienced by a moving observer, every bit as valid as anyone else's. Einstein threw away the ether entirely and kept only the relationships between observers, and in doing so he turned a set of correction factors into a new understanding of reality. It is a humbling lesson about how discovery works. Lorentz and Fitzgerald had the equations. They could have written down every prediction relativity makes. What they lacked was the willingness to believe that space and time were the things actually bending, rather than some material caught in an invisible wind. Einstein's leap was not in the algebra, but in the meaning, in trusting the equations enough to let go of the comfortable world behind them. These were no longer abstract formulas, they made hard predictions about real, measurable things, and one of the cleanest confirmations would come from tiny particles created high in the sky, falling toward the ground. The proof that moving clocks really run slow falls on your head all the time, quietly, from the upper atmosphere. High above the Earth, around 15 kilometers up, the air is constantly struck by cosmic rays, fast particles from deep space, mostly the bare nuclei of atoms hurled out by distant stars and violent events across the galaxy. When one of these slams into the nucleus of an atom in the upper air, it shatters it and sets off a shower of new particles. Among the debris are tiny, short-lived particles called muons, which are heavier cousins of the electron, identical in charge but about 200 times more massive. The muon is unstable. Once made, it survives only a fleeting instant before it decays into lighter particles. We know exactly how long a muon lasts, because we can make muons in laboratories and watch them die. A muon at rest survives, on average, about 2 millionths of a second, 2 microseconds, before it falls apart. That is its natural lifespan, measured countless times, a fixed property of the particle. After a couple of microseconds, give or take, a muon is gone. Now do the arithmetic that should make this story end in disappointment. The muons are born about 15 kilometers up, and they come streaking down toward the ground at very nearly the speed of light, about as fast as anything with mass can go. In 2 microseconds, its natural lifetime, even something moving at nearly the speed of light can travel only about 600 meters. 600 meters, not 15,000. By that reckoning, the muons should die high in the atmosphere, kilometers above our heads, decaying long before they ever reach the ground. Almost none should make it down to where we stand, and yet they pour down in great numbers. Hold out your hand and muons from the sky pass through it at a steady rate day and night. Detectors at sea level, and even deep underground in mines, catch them in abundance. Far, far more muons reach the surface than the simple calculation allows. By the old physics, with time the same for everyone, this is simply impossible. The particles do not live long enough to make the trip. Relativity dissolves the impossibility cleanly, and you can tell the story from either side. From our point of view on the ground, the muons are moving at nearly the speed of light, so their internal clocks run slow. Their 2-microsecond lifespan, stretched by time dilation, becomes long enough from our frame for them to survive the full fall to the surface. The faster they move, the more their clocks slow, and the farther they travel before decaying. The slowing is not a small correction here. It is a large factor, enough to turn 600 meters into 15,000. From the muon's own point of view, nothing about its lifetime has changed. It still lives its ordinary 2 microseconds, ticking along as muons always do. But from the muon's frame, it is the Earth that is rushing up to meet it at nearly the speed of light, and the atmosphere ahead is length contracted, squeezed thin along the direction of motion. The 15 kilometers shrinks to a few hundred meters, a distance the muon can easily cross in its short natural life. Both pictures agree on the only thing that can be checked, that the muon reaches the ground. One side explains it with stretched time, the other with shrunken space. This is not a delicate laboratory effect teased out at the edge of measurement. It is a steady rain of particles confirming relativity over our heads every second, and it was measured directly as early as the late 1930s. Time dilation and length contraction are not interpretations, they are facts, written in the count of muons reaching the ground. And that brings us to the one kind of time that every observer, however they move, can finally agree about. With time stretching and length shrinking, with observers disagreeing about durations and even about what happens at the same moment, it might seem that nothing about time is solid anymore, that everything has dissolved into a matter of viewpoint. But that is not quite right, and the thing that survives is the key to everything still ahead. Amid all the disagreement, there is one measure of time that everyone agrees on, one number that comes out the same no matter who calculates it. Physicists call it proper time, and it is the only aging that is truly real. Proper time is simple to state. It is the time measured by a single clock that is actually present at two events, carried along the path between them. Picture a clock that travels from one event to another, a spaceship leaving Earth and arriving at a distant star, with a watch on board the whole way. The time that watch reads out, the time that actually elapses for the clock making the journey, is the proper time along that path. It is the time the traveller genuinely lives through, the aging their body really undergoes, the seconds their heart really counts. Here is what makes it special. Other observers, watching that journey from different states of motion, will disagree wildly about how long it took and how far it went. To one, the trip lasted years. To another, moving differently, a different span. They will split the explanation differently between stretched time and shrunken space. But every single one of them, if they take their own measurements and compute what the travelling clock should read, will arrive at the same answer. They all agree on the proper time, on what that one onboard watch actually shows when it arrives. The journey looks different to everyone, but the reading on the clock that made it is something the whole universe can agree on. This is why the famous puzzle of the twins is not really a paradox. One twin stays on Earth, the other flies to a distant star at near light speed and returns. When they reunite, the travelling twin is genuinely younger, having aged less. People sometimes object that by relativity each twin sees the other's clock running slow, so why should there be any difference at all when they meet? The resolution is that the situation is not symmetric. The stay-at-home twin moves steadily, in a single frame the whole time. The travelling twin must turn around to come back, and that turning means speeding up and slowing down, breaking the symmetry. Their two paths through space and time are different paths, and proper time, The actual time elapsed depends on the path taken. The travelling twins' path simply carries less proper time. The younger age is not an illusion. It is the proper time along the route they flew. The deep idea hiding here is that time is something more like distance travelled than like a universal ticking. Two people can drive from the same city to the same city by different roads and put different mileage on their cars, and no one finds that strange. The odometer reading depends on the route. Proper time is the odometer of a clock through space and time, and different routes between the same two events rack up different amounts of it. The straightest, most leisurely route through space-time, oddly, racks up the most proper time of all. So time has not dissolved into pure opinion after all. The universal clock of Newton is gone, but in its place stands something firmer and stranger, a time that belongs to a path rather than to the whole cosmos at once. Every clock measures its own proper time along its own route, and that reading is real and agreed upon by all. This single idea, that time is the length of a path, is the doorway to a deeper picture, one in which space and time are no longer separate things at all, but two aspects of a single fabric. For a few years after 1905, relativity was a set of strange, correct predictions without a single clear picture to hold them in. The image that finally tied it all together came not from Einstein, but from one of his former teachers, a mathematician named Hermann Minkowski. Minkowski had taught Einstein in Zurich, and had not, by his own cheerful admission, thought his student especially diligent. Yet it was Minkowski who, in 1908, found the way of seeing relativity that made its strangeness feel almost inevitable. He saw that space and time should be stitched together into a single four-dimensional fabric, which we now call space-time. Begin with how we ordinarily think of the two. Space has three dimensions, the three independent directions in which you can move, left and right, forward and back, up and down. Time seems entirely different, a separate thing, flowing along on its own, the same for everyone, with no relation to the dimensions of space. Minkowski's insight was that relativity only makes sense if you stop treating time as separate and instead treat it as a fourth dimension, woven together with the three of space into one unified whole. An event is not just a place, it is a place at a moment, specified by four numbers, three for where and one for when. Once you make this move, the disagreements between observers fall into a clean and beautiful order. Recall that observers in motion disagree about lengths in space and about durations in time. One sees a longer distance and a shorter time. Another sees a shorter distance and a longer time. Minkowski saw that they are doing something very much like looking at the same object from different angles. Imagine a pencil held in the air. Look at it one way and it casts a long shadow on the floor and a short one on the wall. Turn it and the shadows trade lengths. The pencil itself never changed, only how its single length divided between the two shadows changed with your point of view. Space-time works the same way. Different observers, moving differently, slice the single fabric of space-time into space and time along different angles. One observer's slicing assigns more of an interval to space and less to time, another's assigns it differently. What looks like a disagreement about separate space and separate time is really just two viewpoints on one unchanging four-dimensional reality, carved up two different ways. The space and the time are like the two shadows. The space-time is like the pencil, the real thing that does not change. This reframing is more than a tidy picture. It explains why time dilation and length contraction always come paired, always trading off against each other in exactly the right amounts. They are two shadows of one thing. When motion shifts how space-time is sliced, time and space must adjust together, the stretching of one balanced by the shrinking of the other, because the underlying four-dimensional reality stays fixed. The paired effects that seemed like two separate strange facts are revealed as a single fact seen from two sides. Minkowski announced this with a famous flourish, declaring that from then on space by itself and time by itself were destined to fade into mere shadows, and only a kind of union of the two would preserve an independent reality. It was a bold thing to say, and it proved exactly right. Einstein, who had at first regarded Minkowski's reformulation as a needless piece of mathematical dressing, came to see that it was indispensable, and the space-time picture became the natural home of relativity and the essential foundation for the theory of gravity he would build next. So space and time are one cloth, sliced differently by different observers, and on a single fabric like this, there ought to be something that does not change at all when you reslice it, some true measure of the separation between two events that everyone agrees on, just as the pencil's real length stays fixed however its shadows shift. There is, and finding it is the next step. On the flat fabric of space-time, with observers slicing it into space and time, however their motion dictates, there ought to be something underneath that none of them can change, some true separation between two events that comes out the same for everyone. There is, and it is the quiet foundation the rest of this story stands on. Physicists call it the space-time interval, and it plays the same role for events that ordinary distance plays for points in space. Think first about plane distance. Two cities sit a certain distance apart, and that distance does not change just because you measure it facing north or facing east. You might split it into so many miles east and so many miles north, and someone using a tilted map might split the same gap differently, more in one direction and less in the other. But the straight line distance between the cities is fixed. There is a rule for combining the eastward and northward parts, the old relationship of the right triangle, that always returns the same total however you turn your map. The pieces shift with your choice of directions. The whole stays put. The space-time interval is the same kind of fixed total, built from both the distance in space between two events and the time between them. Different observers disagree about the space part because lengths contract. They disagree about the time part because durations dilate. But when each of them combines their own space and time measurements using the special rule of space-time, they all arrive at the identical interval. The disagreements in space and in time are arranged by nature to cancel out exactly, leaving one number every observer shares. The interval is the real separation between two events, and space and time are just the shifting shadows it casts. The rule for combining them carries one strange twist that makes all the difference, and it is worth meeting head-on. For ordinary distance, you add the squares of the pieces. For the space-time interval, you subtract. The time part and the space part enter with opposite signs, the spatial separation pulling one way, and the temporal separation the other. This single minus sign, where you might expect a plus, is what separates space-time from ordinary space, and it is the source of everything that follows. It means the geometry of space-time is not the familiar geometry of a flat tabletop. It is a stranger geometry, in which time and space stand in opposition rather than simply adding together. That opposition has a remarkable consequence. Because time and space enter the interval with opposite signs, they can balance each other out. If the spatial separation between two events and the time separation are matched in just the right proportion, the two parts can cancel completely, and the interval between those events can come out to exactly zero, even though the events are nowhere near each other in space and happen at clearly different times. A zero interval does not mean the events are at the same place or the same moment. It means the spatial gap and the temporal gap are perfectly balanced under that strange subtracting rule. Hold on to that possibility, because it is the seed of the whole answer we are building toward. In ordinary space, the only way 2 points can have zero distance between them is to be the same point. In space-time, two events can be flung far apart and still have zero interval, provided they sit in that exact balance. Something travels along the paths where the interval comes to zero, and it is the one thing in the universe that moves at precisely the speed where space and time cancel. The interval gives us a true shared measure of separation in a world where lengths and durations have come loose. With it in hand, we can draw a map of every event relative to a given moment, sorting all of space-time into the reachable and the forbidden. That map is called the light cone. Take a single event here and now and ask a simple question about it. Of all the other events in the universe, All the other places at times, which ones can you possibly reach? Which ones could possibly have reached you, and which are forever out of touch? The space-time interval, with its strange subtracting rule, sorts every event in existence into exactly these categories, and the picture it draws is called the light cone. It is the map of cause and consequence, of what can affect what, and it falls directly out of the one fixed speed. To draw it, imagine flattening space down to a single horizontal line and letting time run up the page. You sit at the centre at the present instant. Now picture a flash of light leaving you in all directions at once. As time goes on, that flash spreads outward at the speed of light, reaching farther and farther into space. On the diagram, with space across and time up, the expanding edge of that flash traces two straight lines rising away from you, opening upward like the sides of a V, or in full three-dimensional space, the surface of a cone opening into the future. This is the future light cone, and its slope is set by the speed of the light. Everything you could ever influence lies inside that future cone. To affect a distant event, something must travel from you to it. A signal, a push, a particle, a beam, and nothing can travel faster than light. So only the events inside the cone, close enough in space to be reached within the available time, are within your power to touch. Events outside the cone are too far away in space for any signal from you, even one moving at the full speed of light to arrive before they happen. They lie beyond your reach entirely. The same picture runs the other way, downward into the past. Below you opens a second cone, the past-like cone, holding every event that could have sent a signal reaching you by now. Everything that has ever influenced you, every photon that has entered your eye, every force that has shaped this moment, came from inside that past cone. Anything outside it could not have reached you yet, and so cannot be part of your past in any way that matters. Between the two cones, neither future nor past lies a vast region physicists call elsewhere. These are the events too far away in space to be reached from you, or to reach you at the speed of light. You cannot affect them, and they cannot affect you. Not now, not by any means. They are real events, happening in the universe, but they are causally sealed off from this moment in a present that is not a single slice, but a whole region of mutual unreachability. A star many light years away, as it is at this very instant, sits in your elsewhere. You cannot know its current state or be touched by it. Only its past, the light that left it years ago, sits inside your past cone. The boundary between the reachable and the forbidden, the surface of the cone itself, is built entirely from the paths of light. That edge is not a region with width. It is the precise dividing line traced by beams travelling at exactly the speed of light, the fastest anything can go. Matter, which always moves slower than light, follows paths that stay inside the cone, tilted but never reaching the edge. Light alone rides the surface, so the light cone divides all of space-time into past, future, and the unreachable elsewhere, and the walls of that division are made of light's own trajectories. To understand what light experiences, we have to climb onto that surface and follow the exact path a single beam carves through space-time. The surface of the light cone is not an abstract boundary drawn for convenience. It is the actual path that light follows through space-time, and tracing that path carefully is what finally brings the whole question into focus. Every beam of light, every photon, travels along this surface, along what physicists call a null line, and the word null is the first clue to where we are heading. It means zero, and it refers to the space-time interval along light's path. Set a photon loose and follow it on the diagram with space across and time up. The photon moves through space, so it travels sideways on the map. It also moves through time, so it travels upward. Because it goes at exactly the speed of light, it covers a certain distance in space for each tick of time in the precise ratio the speed of light sets. On the diagram, that fixed ratio means the photon's path is a straight line tilted at a constant angle. the same angle that forms the wall of the light cone, the photon traces the edge exactly. It is, in a sense, the thing that defines the edge in the first place. Now compare that path to the path of anything with mass, anything slower than light. A spaceship, a planet, a thrown ball, you sitting in your chair, all move through space-time too. Even sitting still, you travel up the diagram, advancing through time while staying put in space. Set in motion, your path tilts over, leaning sideways as you move through space as well as time. But because nothing with mass can reach the speed of light, your path can never tilt all the way to the angle of the light cone's wall. It always stays steeper, more upright, tilted somewhat but never reaching the edge. Your path leans toward the cone but stays safely inside it. Light's path lies flat against the boundary itself. This is the deep difference between light and everything else, drawn as plainly as it can be drawn. Things with mass move through space-time along paths that stay inside the light cone, always more time than the limit allows space. Light moves along the cone's surface, along the one set of paths where the tilt is maximal, where space and time are traded in the most extreme possible ratio. There is no path more tilted than light's, because there is no speed greater than light's. The null line is the edge of what is possible, and light lives exactly on it. The name null, meaning zero, points at the space-time interval measured along this path, and here the strange subtracting rule from before does its decisive work. Recall that the interval combines the space part and the time part with opposite signs, so that they can cancel. Along light's path, the amount of space covered and the amount of time elapsed stand in exactly the ratio set by the speed of light, which is precisely the ratio that makes the two parts cancel completely. The spatial separation and the temporal separation, plugged into the rule, subtract to nothing. The interval along any stretch of a light beam's journey is zero. That is what null means. Light travels along the paths of zero interval, the only paths in all of space-time where the separation between start and end comes out to nothing at all. This is no longer a loose possibility. It is a fact about the geometry, forced by the constant speed of light and the minus sign in the interval. The beam that crosses a room and the beam that crosses the galaxy both travel a path whose total space-time interval is exactly zero. The next step is to see, slowly and concretely, just why that cancellation happens, so the zero stops being a formula and becomes something you can picture. It is worth slowing all the way down to see, in plain terms, why the space-time interval along a beam of light comes out to exactly zero, because this single fact is the hinge the whole title turns on. We have the rule that the interval subtracts the space part from the time part rather than adding them. We have the path, that light covers space and time in exactly the ratio set by its own speed. Putting those two together is all it takes, and it can be done without a single symbol. Start with how the interval is built. Between any two events, there is a gap in time and a gap in space. For two ordinary events, you would expect to combine these into a total separation. The space-time rule says to take the time gap, take the space gap, and combine them with a subtraction, the time part counted positive and the space part counted against it. When the time part is larger, the interval is time-like, the kind of separation a slower-than-light traveller can bridge. When the space part is larger, the interval is space-like, a gap too wide to cross even at light speed. The dividing case, the exact balance between them, is where the two parts are equal and the subtraction leaves nothing. Now bring in light's path. Light always covers a fixed amount of space for a given amount of time, set by its one speed. Measure the journey in matching units, the way physicists often do, counting distance in light seconds and time in seconds, so that light travels exactly 1 unit of space for every 1 unit of time. In those units, a beam that travels for a certain stretch of time crosses exactly the same number of units of space. The time gap and the space gap along light's path are equal, always, by the very definition of light speed. Light moving for 10 seconds crosses 10 light seconds of space. The two numbers match precisely. Feed those matched numbers into the subtracting rule, and the result is immediate. The time part and the space part are equal, and the rule subtracts one from the other, so they cancel and leave 0. There is nothing left over. However long the beam travels, however far it goes, the space it covers and the time it takes are locked in the one ratio that makes the interval vanish. A beam crossing a room and a beam crossing the entire visible universe both have a space-time interval of exactly 0, because in both cases the space covered and the time taken stand in that same perfect balance. This is why the boundary of the light cone is special, and why light alone rides it. For anything slower, the time part wins, and the interval is real and positive, a genuine separation in space-time. For light, the two parts are forever matched, and the separation collapses to nothing. The faster a thing moves, the more its path tilts toward this balance, and the smaller its interval becomes for a given trip. At the very limit, at the speed of light, the balance is exact, and the interval reaches 0. Light is the only thing that sits at that limit, so light is the only thing whose path through space-time sums to nothing. There is no trick in this and no sleight of hand. It is simple arithmetic once the rule and the path are in front of you. Equal parts, subtracted, give 0. The strangeness lives not in the calculation but in what the calculation describes. A real journey across real distance whose total separation in space-time is genuinely, exactly nothing. The space-time interval is closely tied to the time a clock actually feels along its path, the proper time we met earlier. So if the interval along a beam of light is 0, then the proper time along that beam is 0 too. That is the claim the title makes, and it is time to say it as plainly as it can be said. Here is the heart of it, stated as plainly as it can be. For light, the proper time along its own path is exactly 0. The clock that light would carry, if light could carry a clock, never advances. From emission to absorption, across whatever distance and whatever span of our time, the beam itself logs nothing, not a fraction of a second. The journey, measured by the beam's own reckoning, has no duration at all. We have earned this carefully, so let it settle without rushing. Proper time is the time a clock actually feels as it travels between two events, the real aging along a path, and it is tied directly to the space-time interval along that path. A large interval means a clock ages a great deal, a small interval means it ages little. We have just seen that the space-time interval along any beam of light is exactly 0, because the space it covers and the time it takes are forever locked in the one ratio that makes them cancel. 0 interval means 0 proper time. The two statements are the same statement. A path of 0 interval is a path along which no proper time passes. So picture the sunlight from the very first chapter once more, the warmth on your face. From your point of view on the ground, that light took a little over 8 minutes to cross from the sun to your skin, a real span you could measure on any clock. But ask how much time passed for the light itself, along its own path, and the answer is none. The photon that warmed you was, by its own measure, absorbed at the very instant it was emitted. The 8 minutes are entirely yours, a feature of your slower path through space-time. For the light, emission and arrival are not separated by any lived duration at all. Stretch the journey as far as you like, and the answer does not change, which is the most startling part. A photon that left a galaxy at the far edge of the visible universe, travelling toward us for over 13 billion years by our clocks, ages by exactly the same amount as the sunlight crossing your kitchen, which is to say, not at all. 13 billion years of our time, the entire history of stars and planets and life unfolding while it travelled, and for the photon, no time whatsoever. It is emitted and absorbed in the same instant by its own reckoning, however vast the gulf it crossed in hours. Distance and duration, so real to us, fold to nothing along the null path. This is the literal content of the title, no longer a poetic flourish, but a direct reading of the physics. Light has never experienced a single moment, because experience, in the only sense relativity can give the word, is the passage of proper time, and light's proper time is zero on every journey it has ever made. The whole life of a beam, from the moment it leaves its source to the moment it is swallowed by an eye or a detector or a leaf, occupies, for the beam, no span at all. Every photon arrives, in its own terms, the instant it departs. It is a fact, clean and well-grounded, sitting at the end of a chain of plane steps, each resting on the one before. The constant speed of light forced time and space to bend. The bending gave us the space-time interval. The interval along light's path is zero. Zero interval is zero proper time. There is no escape hatch in the logic and no hidden assumption, and yet the moment we say light experiences zero time, a quiet warning sounds. Because to even speak of the light's experience, we have been imagining riding along with it, sitting in its frame. That, it turns out, is the one thing relativity flatly forbids. There is a catch hiding in everything we have just said, and honesty requires meeting it directly. All through the last few chapters, the picture in your mind has probably been of riding along with the beam, sitting in the photon seat, looking out from the light's own point of view and finding that no time passes there. It is a natural and useful image, and it points at something true, but taken literally, it is forbidden. According to relativity itself, there is no such seat. Light has no point of view. You cannot ride the beam. The reason follows from the very effects we built up earlier, pushed to their breaking point. Recall how things change as you approach the speed of light, watched from outside. Time dilation grows without limit, the moving clock slowing further and further toward a standstill. Length contraction grows too, the moving object squeezing flatter and flatter along its motion. These effects are gentle at low speeds and dramatic near light speed, governed by that factor which climbs toward infinity as the speed approaches that of light. The key word is approaches. The equations describe getting closer and closer to light speed. They do not describe arriving. Try to imagine actually reaching the speed of light, and the mathematics does not give a strange answer. It gives no answer at all. The factor that governs time dilation and length contraction does not settle on some large number at the speed of light. It breaks, dividing by zero, returning nothing meaningful. Time dilation would be infinite, every duration stretched beyond any value. Length contraction would be total, all distance along the direction of motion squeezed to nothing. A frame of reference moving at the speed of light is not a frame with extreme properties. It is not a valid frame at all. The construction simply falls apart. This is not a gap in our knowledge or a problem awaiting a cleverer theory. It is built into the structure of relativity. The theory is constructed for observers who move slower than light, and every observer it allows must move slower than light. There is no rest frame for a photon, no vantage point that travels along with the beam from which the universe could be observed. The question, what does the universe look like to a photon, has no answer within the theory, because the theory forbids the standpoint the question assumes. So when we say light experiences zero time, we are speaking carefully, and the care matters. We are not reporting the view from inside the beam, because there is no inside to view from. We are saying something we can state entirely from our own legitimate slower-than-light frames. We compute the proper time along the path a beam follows through space-time using the interval, and that proper time comes out to zero. Proper time is a property of a path, and it can be calculated for the light's path without ever climbing a board. The zero is real and frame-independent. What does not exist is the photon's own perspective on that zero. The distinction is subtle, but it keeps us honest. The proper time along the null path is genuinely zero, agreed upon by every valid observer. That is solid physics. The further step of imagining the photon sitting in its own frame and experiencing that zero as a lived now quietly assumes a frame that relativity does not permit. The truth is the cleaner and stranger of the two. The path carries zero proper time, and there is no traveller riding it to notice. This limit was not discovered late, as a technical caveat. In a sense, it was the beginning of the whole theory, because the young Einstein arrived at relativity by asking exactly this forbidden question, imagining what it would be like to chase a beam of light and ride alongside it. Long before the patent office, before the famous papers, Albert Einstein was a teenager turning a single question over in his mind, and that question grew into the seed of everything. He was about 16, by his own later telling, when he began to wonder what it would be like to chase a beam of light and catch up to it, to run alongside the wave and travel at its speed. It is the kind of daydream many young people have and let go of. Einstein held on to it for 10 years, and in holding it he found that it would not let the rest of physics stay as it was. Picture the thought as he did. Imagine running faster and faster after a beam of light until you match its speed and ride beside it. What would you see? By the ordinary rules of his day, the rules of waves and motion that everyone accepted, the answer seemed clear. If you travelled alongside a light wave at exactly its speed, the wave would appear frozen next to you, standing still. Its peaks and troughs, which normally race forward, would hang motionless in space beside you, a wave that does not move. You would see a stationary pattern of electric and magnetic fields, sitting frozen in the air. The trouble is that no such thing can exist. Maxwell's equations, the same equations that revealed light to be an electromagnetic wave, do not allow a frozen light wave. A static, standing pattern of electric and magnetic fields going nowhere is not a solution those equations permit. Light, according to the very laws that describe it, must always move at its one speed. It is never at rest. So the rules of motion seem to promise something, a frozen wave that the laws of electromagnetism flatly forbade. The two pillars of physics disagreed about what the boy chasing light would see. That contradiction is the crack the whole theory grew from. Einstein could not accept that the laws of light should change just because you ran fast enough to keep up. It seemed deeply wrong that catching up to a beam would let you see something, a frozen wave, that nobody standing still could ever see, something the laws themselves prohibited. The principle that the laws of physics should be the same for everyone in steady motion told him the frozen wave must be impossible for the runner too. And if you can never catch the wave, never bring it to rest beside you no matter how fast you run, then light must always retreat from you at full speed. The chase can never be won. This is the constancy of the speed of light, arrived at not from an experiment, but from a boy's stubborn refusal to accept a contradiction. The speed of light is the same for everyone because the alternative, catching it and freezing it, breaks the laws of electromagnetism. Einstein took the impossibility of riding the wave as a clue to how the universe is built, and built relativity to honour it. The young man's daydream of catching light became the grown man's principle that light cannot be caught. There is a quiet beauty in how this closes back on itself. The thought experiment that started relativity imagined riding alongside a beam of light. Relativity, once complete, turns around and declares that this very thing is impossible, that no observer can ever ride the beam. The question that opened the door also revealed that the door leads nowhere you can stand. Einstein chased light in his mind and discovered, in the chasing, that it can never be caught. That light cannot be caught. That it always moves at its one speed and never rests, is tied to one more deep fact about what light is. Light has no mass, and being massless is exactly what forces it to travel at the one speed and no other. Why must light travel at its one particular speed, and never slow down, never stop, never go any slower or faster? The answer reaches into what light fundamentally is, and it comes down to a single property. Light has no mass. A photon, the basic grain of light, is massless, and being massless is precisely what compels it to move at the one speed we have been circling this whole time. Mass and speed are bound together by relativity in a way that leaves light no choice at all. Relativity revealed that mass and energy are two forms of the same thing, captured in the most famous equation in all of science, which relates the energy of an object to its mass through the speed of light. But that famous short form is only part of a fuller relationship, one that ties together an object's energy, its mass, and its momentum, the quantity of its motion. This fuller relationship governs how anything, with mass or without, moves through the world, and it is here that light's strangeness finds its root. For anything with mass, that relationship has a built-in consequence. To move faster, the object must gain energy, and as its speed climbs toward that of light, the energy required climbs faster and faster, heading toward infinity. To actually reach the speed of light, a massive object would need infinite energy, which the universe cannot supply, so nothing with mass can ever reach light speed. It can be pushed closer and closer at ever greater cost, but the final step is forever out of reach. Mass is the thing that holds you back, the anchor that keeps you below the limit. The more mass, the heavier the anchor, but any mass at all is enough to forbid the top speed. Now remove the mass entirely, and the logic flips. A massless particle has no anchor holding it back, nothing requiring infinite energy to reach the top speed. In fact, the same relationship with the mass set to zero says something striking. A massless particle cannot travel at any speed other than the speed of light. It cannot go slower. There is no such thing as a slow photon, or a photon at rest, or a photon dawdling along at half speed. The moment light exists, it moves at its one speed, the full speed, and it can do nothing else. For a massless particle, that speed is not a limit it strains toward, but the only speed it is permitted to have. This closes the loop with the boy chasing light. You cannot catch a photon and bring it to rest beside you, not because photons are fast and you are slow, but because a photon at rest is a contradiction in the deeper sense. A massless particle has no rest. Rest is simply not among the things it can do. It is always moving at the one speed, for every observer, which is exactly the constancy we started from. The massless nature of light and the constant speed of light are two ways of saying the same thing, and it ties back to the zero proper time as well. Because light is massless, it must travel at the one speed. Because it travels at that speed, its path through space-time has zero interval. Because the interval is zero, the proper time along it is zero. The chain runs all the way from the absence of mass to the absence of experience time. Light ages by nothing because it weighs nothing. The two facts are joined at the root. We have been speaking of light as a wave and as a path through space-time. But that grain of light, the photon, the massless particle with no rest, deserves a closer look, because turning the smooth wave into a countable grain was its own revolution. We have leaned on the word photon, treating light as a grain, a single countable particle travelling its null path. But that grain was a hard-won idea, and for a long time it sat in direct tension with everything Maxwell had shown. Maxwell's triumph was proving light to be a wave, a smooth, continuous ripple of electric and magnetic fields, spread out and flowing. The photon is the opposite picture. Light as a stream of discrete packets, tiny indivisible grains of energy. How both can be true is one of the deepest turns in physics, and it began with a problem about glowing objects. At the close of the 1800s, physicists were stuck on a question that sounds almost too ordinary to be dangerous. What colour does a hot object glow, and how brightly at each colour? Heat a poker, and it glows red, then orange, then white as it gets hotter. The pattern of light a hot body gives off, spread across the colours, was carefully measured. But when physicists used the trusted wave picture of light to predict that pattern, the theory failed catastrophically. It predicted that a hot object should pour out endless energy at the bluest, highest frequency end of the spectrum, an infinite blaze of ultraviolet that obviously does not happen. The clean wave theory gave a nonsensical answer, a failure striking enough that it earned a dramatic name, the ultraviolet catastrophe. The German physicist Max Planck found the fix in 1900, and he found it almost against his will. To make the math match the measured glow, he had to assume that energy was not emitted smoothly and continuously, as a wave should be, but only in discrete chunks, small fixed packets he called quanta. The energy of each packet depended on the light's frequency, tied to it by a tiny new constant of nature now bearing Planck's name. With energy parcelled into these grains, the predictions snapped into perfect agreement with the glowing poker. Planck regarded the trick as a mathematical convenience, a strange bookkeeping device, and did not quite believe the packets were real. It was Einstein, again in that miraculous year of 1905, who took the packets seriously as physical things. Studying how light knocks electrons out of metal, an effect where dim blue light could free electrons but bright red light could not, he saw that the wave picture failed here too. The behaviour made sense only if light arrived as individual grains, each carrying a fixed bit of energy set by its colour, an electron knocked loose by one whole grain at a time. Einstein proposed that light truly is quantized, made of real particles of energy, and it was this work, not relativity, for which he was eventually awarded the Nobel Prize. The grains came to be called photons, so light is both wave and grain, and the resolution is not that one picture is wrong, but that light is a thing deeper than either everyday image. It travels and spreads and interferes like a wave, yet it is emitted and absorbed in whole packets like particles, each photon carrying a definite energy and momentum but no mass. This double nature, wave and particle at once, became a cornerstone of quantum physics, the strange and successful theory of the very small. Light was the first place the quantum showed itself, the crack through which a whole new physics entered. For our story, the photon is the traveller whose clock we have been reading. It is a massless grain, moving always at the one speed, tracing the null path of zero interval, aging by nothing. Now we can send one of these grains on the longest journey there is, across nearly the whole age of the universe, and ask what such a trip is like. Take a single photon and send it on the longest journey physics knows, to make the zero proper time as vivid as it can possibly be. Not sunlight across 8 minutes, but a grain of light that has crossed nearly the entire history of the universe. Such photons are real, and they are arriving right now. They fill all of space, and they carry a story that stretches back almost to the beginning of time. The early universe, in the moments after the Big Bang, was unimaginably hot and dense, a blazing fog of particles packed so tightly that light could not travel freely. A photon could not fly in a straight line. It was constantly scattered, bounced from charged particle to charged particle, trapped in the glowing murk like light inside thick cloud. For nearly 400,000 years this fog persisted. The whole universe an opaque, radiant haze with light unable to strike out across it. Then the universe expanded and cooled enough for something decisive to happen. The loose charge particles, the bare nuclei and free electrons, joined together into neutral atoms, mostly hydrogen. Neutral atoms do not scatter light the way free charges do, and all at once the fog cleared. The universe became transparent, and the light that had been trapped was suddenly set free to travel in straight lines across open space. That release happened everywhere at once, and the photons set loose in that moment have been flying ever since, for over 13 billion years. We catch them today. They come from every direction in the sky, a faint glow of light left over from that ancient clearing, stretched and cooled by the long expansion of the universe into a whisper of microwaves. We call it the cosmic microwave background, and it is the oldest light there is, a direct image of the universe as it was when it first turned clear. When you tune an old television between channels, a small fraction of the static once came from these very photons, the afterglow of the early cosmos landing in your living room. Now follow one of those photons and apply everything we have built. By our clocks, it has travelled for more than 13 billion years, crossing a span of the universe so vast the number means little. Across that journey, stars were born and died, galaxies took shape, our sun and earth formed, life arose, and you came to be reading this, all while the photon flew. From our point of view, an almost incomprehensible stretch of time and space lies along its path, and for the photon itself, along its own null path. The proper time is 0, the same 0 as the sunlight on your face. This grain of light, released when the universe first cleared, absorbed at last by a detector or an eye 13 billion years later, logged not one instant on its own reckoning. By its own measure, it was emitted in the young hot cosmos and absorbed in our cool, structured ancient one in a single event with no duration between. The oldest light in existence is, by its own clock, no older than the moment it was born. The 13 billion years are entirely ours, written into our longer path through space-time, not its. This is the claim at full stretch, as large as the universe allows. The longest possible journey and the shortest possible sunbeam carry exactly the same lived duration, which is none. Distance and our flowing time fall away completely along the null path, whether the trip is a kitchen or a cosmos. If light's own clock registers nothing across 13 billion years, you might wonder whether the journey leaves any mark on the light at all. It does, and noticing what changes, against the backdrop of what does not, sharpens the whole picture. If a photon ages by nothing on a journey of 13 billion years, it is fair to ask whether the trip touches it at all, whether anything about the light records the passage it made through our time. Something does change, and noticing exactly what it is, set against the 0 proper time, draws the line between the light's own reckoning and ours with real precision. The light does not age, but it is stretched, and the stretching is something we can measure directly. The change is in the light's wavelength, the distance between successive crests of the wave. Light comes in a range of wavelengths, which we see as colour, from the shorter waves of blue through the longer waves of red, and out beyond into the invisible. When light travels across the expanding universe, its wavelength is stretched along the way. The universe itself is growing, the space between distant galaxies steadily widening, and as a photon crosses that swelling space, the wave riding through it is drawn out longer, its crests pulled farther apart. Light that set out as visible, even as energetic blue light, arrives shifted toward the red and beyond, its waves lengthened by the expansion it travelled through. Physicists call this cosmological redshift. The ancient light from the early universe shows this in the extreme. It began as the fierce glow of a hot, dense cosmos, light far more energetic than visible light. Across 13 billion years of expansion, its wavelength has been stretched by a factor of more than 1,000, drawn out from a searing glow into the faint cold microwaves we detect today. The redshift is the fingerprint of the journey, a direct measure of how much the universe has expanded since the light was set free. By reading how far a galaxy's light has shifted toward the red, astronomers measure how much space has grown since that light departed, and so how far away and how far back they are looking. Here is the careful distinction that makes the whole picture honest. The redshift is not the light aging. It is not the photon's own clock advancing, because the photon's clock does not advance at all. The stretching is something that happens to the light as measured in our frame, by us, against our rulers and our sense of distance and time. We see the wave drawn out because the space it crossed expanded in our reckoning of things. The photon, on its null path, still logs 0 proper time. Redshift and 0 aging sit side by side without conflict, because they are answers to different questions, one about what we measure from outside, one about the light's own path. It helps to hold both at once. From our vantage, the photon had a long and eventful trip, stretched and reddened by billions of years of cosmic expansion, carrying in its lengthened wave a precise record of how much the universe grew while it flew. From the standpoint of the null path it followed, there was no trip in time at all, no duration, no aging, emission, and absorption in a single timeless event. The redshift belongs entirely to our description. The zero proper time belongs to the path itself. Both are true, and they do not touch. So the journey does leave a mark, but the mark is on our side of the ledger, written in the colour of the light rather than in any clock the light carries. The one thing that changes is the wavelength, and even that change is something we attribute, not something the photon experiences. This points at the strangest framing of all, the one the whole subject keeps circling. For the photon, emission and absorption may be in the deepest sense a single event. There is a way of stating light's situation that sounds almost mystical, but follows directly from the zero space-time interval, and it is worth setting down plainly while staying honest about what it does and does not mean. For a beam of light, the moment of emission and the moment of absorption are, along its own path, separated by nothing. Zero interval, zero proper time, zero separation in the only measure that belongs to the light itself. In the geometry of space-time, the point where the photon is born and the point where it dies are, by the light's own reckoning, the same point. Leaving and arriving are one event. Let this sit against our ordinary experience where it sounds impossible. To us, a photon is emitted at one place and time, say the surface of a distant star long ago, and absorbed at another place and time, perhaps you're right tonight, with a vast gulf of space and years between. Two clearly separate events, far apart. But that separation is measured along our paths, with our clocks and rulers. Along the photon's own null path, the space-time interval between those two events is exactly zero, and an interval of zero means there is no separation at all in the light's own terms. The two events that look so distant to us are, to the path connecting them, adjacent, touching, one. This is not a claim that emission and absorption are literally the same event in our world. They plainly are not. The star and your eye are real and really far apart, and the light really did cross between them. The statement lives entirely in the geometry of the null path. It says that the measure of separation appropriate to light, the space-time interval along its trajectory, vanishes, so that by that measure the start and end coincide. It is a fact about the strange ruler of space-time, not a denial of the obvious distance we observe. Some physicists have taken this geometry seriously enough to build pictures of light on it, treating the emission and absorption of a photon as a single connected happening rather than two separate ones bridged by a journey. In these pictures, the photon is less a tiny ball flying across the gap, and more a direct link between the place it leaves and the place it lands, a connection stitched along a path of zero interval, with no real travel in between from the light's side. The light does not so much cross the distance as join its two ends. Whether such pictures are the right way to think about light remains a matter of interpretation, not settled fact, and careful physicists hold them loosely. What is not a matter of interpretation is the geometry underneath. The interval along the light's path is zero. That is solid. From that zero follows the strange adjacency of emission and absorption in the light's own terms. That follows cleanly. The further step of imagining what this means for what light is, of picturing the photon as a single timeless link rather than a traveller, is where physics shades into interpretation, and where careful people disagree. We can state the geometry with confidence and hold the picture with humility. There is one grand picture of the universe in which all of this feels less paradoxical, a way of seeing time itself that takes the space-time fabric completely literally. In it, the past and future are as real and as fixed as the present, every moment simply there, and light's timelessness becomes one feature among many of a universe that is, in a sense, already complete. There is a way of picturing the whole universe in which light's timelessness stops seeming like a special oddity and becomes a natural feature of how everything is laid out. It follows from taking Minkowski's space-time completely at its word, treating the four-dimensional fabric not as a helpful diagram, but as the literal reality. In this view, called the block universe, all of time already exists, every moment laid out at once, the past and the future as real and as fixed as this present instant. Nothing flows. Nothing comes into being or passes away. The universe simply is, complete, in 4 dimensions. The idea grows from relativity's treatment of time as a dimension much like space. Think of how you regard space. The far side of the world exists right now, even though you're not there. Distant places are all equally real, laid out together, and you simply occupy one spot among them. The block universe says time is the same. The distant past and the far future exist, laid out along the time dimension, all equally real, and you simply occupy one moment among them, the one that feels like now. Your sense that this moment is uniquely present, that the past is gone and the future not yet made, is, in this picture, a feature of your vantage point, not a fact about the universe. Relativity gives this strange idea real support through the relativity of simultaneity we met early on. Recall that observers moving differently disagree about which events happen at the same time, about what counts as now. There is no universal present slicing across the universe. Your now and another's now contain different events. If there is no single agreed-upon present moment, it becomes hard to say that only the present is real and the rest is not, because there is no shared present to privilege. Different observers would disagree about which events are real now. The cleaner view is that all events are equally real, and present is just a label each observer attaches to their own slice. The universe is the whole block, not a moving edge of now. In this picture, your life is a fixed shape in space-time, a long thread running from your birth to your death, every moment of it equally present somewhere along the thread. The feeling of time passing, of one moment giving way to the next, is something about how consciousness moves along the thread, not a property of the thread itself. The block is static and complete. The flow is in the experiencing, not in the universe. Now light fits in without strain. A photon's path through this block is a null line, a thread of zero length in space-time connecting its emission to its absorption with no proper time between. In a block universe, where all moments coexist, a photon is simply a line laid down across the fabric, joining 2 points that, by its own measure, are not separated at all. Its timelessness is not a riddle, but a plain consequence of the geometry of the block. The photon does not experience zero time because it races so fast that time stops. It is a zero-interval thread in a structure where time does not flow for anything, only seems to flow for those of us moving along time-like paths. Whether the block universe is the true picture is not settled, and thoughtful physicists and philosophers line up on different sides. It follows naturally from taking relativity literally, yet it sits uneasily with our vivid sense of a passing now, and with parts of physics where time seems to have a direction. It is a serious interpretation, not a proven fact, and it is offered here as one coherent way the pieces can fit, held with the same humility as before. The block universe leans on taking light's timelessness fully literally, and that is exactly where we should pause, because the word experience, which the title uses, may be straining past what the physics can actually bear. It is time to be fully honest about the language, because the title uses a word that the physics cannot quite support, and noticing exactly where the words run out is part of understanding the idea rather than a retreat from it. The title says light has never experienced a single moment in time. The physics gives us something precise and solid underneath that phrase, but the word experienced is doing work that relativity does not license, and the gap between them is worth seeing clearly. Here is what the physics actually says, stated without metaphor. The proper time along any light beam's path through space-time is zero. This is a statement about a path, computed from the space-time interval, and it is true and agreed upon by every valid observer. There is no controversy in it. The trouble is only with translating that clean geometric fact into the language of experience, of a point of view, of something it is like to be the light. The difficulty is the one we met when we said you cannot ride the beam. Experience in any ordinary sense implies a perspective, a frame from which the world is encountered, a now that is lived through. Relativity flatly denies light any such frame. There is no rest frame for a photon, no vantage point travelling along with the beam, no standpoint from which the universe could be experienced as timeless or any other way. So to say light experiences zero time is to attribute an experience to something the theory says has no perspective at all. The phrase smuggles in a viewpoint that the physics has carefully ruled out. This is why careful physicists tend to avoid saying that light experiences anything. The honest statement is geometric, not experiential. We can say the proper time along the light's path is zero. We can say that by the measure of space-time interval, emission and absorption are not separated. We cannot really say what the light experiences because experience needs a someone or something doing the experiencing from a point of view, and light has no point of view to do it from. The zero is real. The experience is a way of speaking, a human handle on a fact that does not truly fit the shape of experience at all. None of this makes the title wrong so much as makes it a doorway. It takes a true and remarkable fact, the zero proper time along light's path, and dresses it in the language of experience because that is how human beings reach for strange truths, by imagining ourselves inside them. The imagining is how we got here, how Einstein got here, chasing a beam in his mind. It is a fine way to arrive at the idea, as long as we set the imagining down at the end and keep the clean fact, which needs no point of view to be true. So let the limit stand as part of the answer rather than a footnote to it. Light does not experience timelessness, because there is no light's eye view to hold an experience. What is true is stranger and quieter. The path light follows through space-time has zero proper time, full stop, with no traveller aboard to find it short or long. The universe contains paths along which no time passes, and light follows them, and there is no one riding them to notice. The phrase reaches a little past the physics, and seeing exactly where it reaches too far is itself the deepest part of understanding it. Where the firm physics runs out, the open questions begin, and there are real ones, places where this whole picture still has unsettled edges that honest curiosity should know about. The picture we have built is among the most thoroughly tested in all of science, confirmed by muons in the sky, by precise clocks flown on aircraft and satellites, by particle accelerators that push matter to a hair's breadth below light speed every day. But honest curiosity should know where the edges are still open, the places where the clean story meets real uncertainty. There are a few, and naming them keeps the wonder grounded rather than letting it harden into false certainty. The first concerns the very thing the whole argument rests on, that light is massless. Everything we have said depends on the photon having exactly zero mass, which is what forces it to travel at the one speed and gives it a zero interval path. The best theory of light treats the photon as massless, and every measurement is consistent with that. But measurements can only ever set a limit, never prove an exact zero. Experiments have shown that if the photon has any mass at all, it is fantastically small, smaller than a tiny fraction of the mass of any other known particle, almost unimaginably light. The bound gets tighter over time, but it can never reach absolute zero. If the photon did have some minuscule mass, it would travel just below the universal speed. Its path would carry a tiny but non-zero proper time, and much of what we have said would hold only as an extraordinarily good approximation, rather than an exact truth. The evidence strongly favours a massless photon, yet the door cannot be closed all the way. The deeper unsettled edge is that relativity is not the whole story of nature, and we know it. Special relativity describes space-time beautifully, but it does not include gravity. For that, Einstein built the larger theory of general relativity, in which space-time curves and bends, and general relativity, for all its triumphs, does not fit together with quantum physics, the equally well-tested theory of the very small that gave us the photon in the first place. The two greatest theories of the 20th century, one of the large and one of the small, contradict each other in the situations where both should matter, such as inside black holes or at the universe's first instant. Physicists have sought a theory of quantum gravity to unite them for generations, without success. What this means for our story is a quiet humility about the foundations. The smooth, continuous space-time that lets us draw the light cone and compute a clean zero interval may itself be an approximation, an emergent picture that breaks down at scales far smaller than any we can probe. If space-time is grainy or woven from something deeper at the tiniest scales, then the notion of a perfect null path with exactly zero interval might be an idealization, true at every scale we can reach, but not the final word. We do not know. The light cone may be exact, or it may be the large-scale face of something stranger underneath. There are open questions about light itself in quantum terms too, about how a single photon's path should even be described when quantum physics blurs the very idea of a definite trajectory. The clean line we drew across space-time is a classical picture, and the quantum reality of a photon is subtler, more spread out, harder to pin to one path. None of this unsettles the core result at the scales we live and measure in. The zero proper time along light's path is as solid as physics gets for everything we can test. The open edges lie deeper down, at the smallest scales and the most extreme places, where our best theories themselves fall silent. That is the honest shape of it, a firm answer surrounded by real and acknowledged mystery. So let us go back to the warmth on your face and answer the question we started with in the simplest words we have. The light touching your skin left the sun about 8 minutes ago by your clock and mine, but along the path that light travelled, no time passed at all. Not 8 minutes, not a second, nothing. The proper time along a beam of light's journey is exactly zero, whether the trip is from the sun to your face or from the edge of the visible universe to your eye. That is the whole answer, earned step by step, and it is true. We can say now precisely what it does and does not mean. It does not mean light sits in some frozen vantage point watching a timeless world, because relativity allows light no vantage point at all. It means something cleaner and stranger. The universe contains paths along which the space-time interval is zero, and therefore the proper time is zero, and light follows exactly those paths, with no traveller aboard to find the journey short or long. The 8 minutes are yours. The zero belongs to the path. Trace back how we got here, because the chain is worth holding whole. Light is fast but finite, caught first in the late arrivals of Jupiter's moon. It is a wave of electricity and magnetism, with one fixed speed written into Maxwell's equations. That speed turned out to be the same for everyone, no matter how they move, and to keep it fixed, time and space themselves had to bend, stretching and shrinking in exact proportion. Bending time and space joined them into one fabric, space-time, with a single true measure of separation, the interval. Along light's path, that interval is zero, because light covers space and time in the one ratio that makes them cancel. Zero interval is zero proper time. Every link plane, each resting on the one before, now widen out from the warmth on your skin to the light all around you, because once you hold this, the ordinary world looks different. Every photon entering your eye right now, from this screen, from the lamp, from the window, has travelled a path of zero proper time to reach you. The light from your own hand, the light from the farthest star you can see on a clear night, the ancient glow left over from the universe's first clearing, all of it arrives by its own reckoning in the same instant it departed. You are bathed, constantly, in light for which the journey to you took no time at all. The sky full of stars is a sky full of zero-interval threads, reaching across billions of years that the light itself never counted. There is a strange comfort in this, and a strange grandeur. The same physics that makes time stretch and length shrink, that breaks the universal now and weaves space and time into one cloth, also tells you that the messengers carrying the universe to your eyes are, in their own terms, untouched by the vast distances they cross. The light from a star that may no longer exist still reaches you fresh by its own clock, emitted and absorbed in a single timeless event, with all the intervening years belonging to the space between, not to the light. You see the universe by the grace of these timeless threads. You are part of the same fabric they travel through, a slower path of your own, accumulating proper time, aging through your one thread across the block of space-time, while light lays its zero-length lines across the whole of it. The next clear day, when you turn your face to the sun and feel that warmth arrive as if instant, you will know that for the light, it truly was instant, and that the 8 minutes were the universe handing you, gently, a little piece of its deepest geometry, free for the feeling. That is what light is, and that is why it has never known a single moment in time.